Okay, I'm going to take a little bit of a mention about air resistance, and the book does a pretty good job of it. So I'll mainly let the book do the explanation. I'll just like touch on a couple of things. Again, we have an object moving through air, and now simple viscosity, the force is minus BV. But for air resistance, it's more complicated. That's because air is compressible in front and rarefied behind. So that means the air is thicker in front as you go through and thinner behind. So that means it's like suction on behind, and you have to push through thicker air. So that means it's more energy to push through. So that limits your top speed if you have a certain amount of thrust. And now that's actually the interesting thing about like NASCAR or something, is that they will sometimes race nose to tail, and what happens is for the car that's on the back side, you're not compressing the air in front, and so that means that the air resistance is less. For the car in the front, you're not making the air thinner behind, making suction, so that means that the two cars together, they call this drafting, can actually go faster than one car by itself on the racetrack. Now that's NASCAR. IndyCar is different. With Indy cars or Formula, the Grand Prix type cars, they have wings in the front and the back to provide the downforce. And what happens is that they get really close to one another. Air's not flowing over the wings to provide the downforce, and so they cannot go as fast. So drafting works best with NASCAR and does not work as well for Indy cars. Well, back to this object going through air. Then the resistive force, so the resistive force is equal to, well, it turns out because of how the air behaves, it relates to the velocity squared. So if you go twice as fast, you have 4 times the resistive force. It also depends on the cross-sectional area. So the cross-sectional area, so an object moving, through the air like that actually has less cross-sectional area than something doing this. So you only have to worry about the area that's hitting the air rather than that. And so this type of object would move faster than the object on the right. And so the cross-sectional area matters. Again, if you have a skydiver and they jump out of an airplane, so if they spread wide like this, then what happens is they're gonna have a bigger area than a skydiver that is all curled up in a little ball. So if they're curled up in a little ball, then the area is going to be less, and so they're going to fall faster, and a skydiver like that falls slower. You may have seen some of these skydiving events where a number of people jump out of an airplane and they meet up and form patterns in the sky as they're coming down. Well, the first ones that jump out spread eagle, so they go slower. The later ones actually pull their arms together against their body, so they go faster until they all meet up. This turns out to be very, very dangerous because the closing velocity between the two can be extremely high, and they can actually hit and knock each other out. Air resistance also depends on the density of the air. Air is not a constant density. Air is very easy to compress. It's very easy to rarefy. The density of the air changes with weather. It changes with humidity. It changes with temperature. So it's very much variable. And then it depends on something we call the drag coefficient. The drag coefficient is basically how the air moves past the body. That depends on the shape of the object, and it depends on turbulence as the air goes around. So in other words, a very smooth object, air goes around better than for a rough object. And so a smooth object would have a lower coefficient than a rough object. Now, typically, we define that coefficient not for this equation, but for another equation. And so, for the resistive force, it turns out to be this. Okay, so the resistive force, the air resistance force, is given by 1/2 of the drag coefficient times the density of air times the cross-sectional area times the velocity squared. And so again, the skydiver will fall out of the airplane, and when the velocity, when that r equals mg, so when the downward force equals the upward force, then that means ma is 0. So if ma is 0, then that means that the acceleration is 0, and so that is terminal velocity again. Now, terminal velocity does not mean that the skydiver falls and then starts floating in the air up here. And what it means is that they fall at that same speed for the rest of the way, all the way down to the ground. And so that's that terminal velocity. Now, the terminal velocity can actually work both ways, and that is if you're falling faster than terminal velocity, then the air resistance is bigger than gravity, and so that will slow you down to terminal velocity. This happens with meteorites. When meteorites hit the atmosphere, they're typically going faster than the terminal velocity, and so air resistance slows them down until terminal velocity. This can also happen with skydivers that jump from exceedingly high altitudes. So if they jump from near the stratosphere or something, the air is very thin, and so the terminal velocity is much higher there than it is closer to the ground. And so as they fall into denser air, then the resistance increases and they slow down further. So it turns out that the air resistance can be a very complicated concept. The book does a couple of simple examples with it. It's pretty good, and so I'm going to let the book do most of the explaining here. I explained about simple viscosity, which the book doesn't mention much in this chapter. And I also expanded this to motion and resistive medium in general. And so, which the book kind of hints at, but I don't think they do quite as good of a job.